So today we're going to be talking about stream flow, how basically water is flowing down a stream and how that changes through time and with some changes that we make to streams. So when we think about where the water is coming from, we should think about two sources, basically precipitation and groundwater. Now groundwater is eventually, at some point was precipitation, right? Rain hits the ground, goes in, some of it infiltrates into the sediment, into the soil, and goes down into the groundwater, and some of it runs over land. Now the differences between like where we see a stream having precipitation or groundwater can make important ecological differences within the stream, especially with things like temperature, which we'll see here in a bit. So let's talk about rain hitting the ground in a watershed. What happens is it starts to fill up those pore spaces, okay? Now those pore spaces, are those little areas in between the individual sediment particles. And depending on what type of sediment we have, that those pore spaces get filled up faster or slower, okay? So if we have, like, let's say a really hard rain, what you get is a maximum infiltration rate, okay? Let's start with just a really light rain, okay? And if you just get a really light rain that's happening on and off within the day, you never get like water flowing through the streets. And that the reason that is because the water is infiltrating into the soil and it's not running over land. It's not running over the flow. But as you increase that precipitation rate, essentially what you get is those pore spaces fill up, and even though like gravity is pulling that water down into the groundwater, it'll eventually outstrip that maximum rate, and then that's where you get runoff over land flowing in a either big sheets or into the rivers, okay? Now if the water is coming from groundwater, let's say a stream has most of its water coming from groundwater, it's really stable, okay? Water might be like thousands of years old, and now that old I put in quotes here, and what that really is looking at is, or what I'm talking about there is, it might have been underground for thousands of years. Now if we look at streams though that have a majority of the water coming from groundwater, what we see is that E here, right? Because we know that, let's say it's a warm summer day, and the water, if it's all coming from precipitation, will have, it'll get cold. So this has been midnight here. It cools off during the nighttime, and then it warms up during the day, and then it starts cooling off at night again, right? And that's because the precipitation that's flowing into the river is running over the land and getting heated up or cooled off by the day and the night. Whereas if you have water coming out from groundwater, you'll see a very slight, there's a slight like temperature wave here going on, but it's very, very slight, because all of that water that's coming out into the stream is pretty cold. It's probably somewhere around like 40 degrees coming out from underground. So this stream D here might be an intermediate, where a decent amount of the water is coming from precipitation runoff and a decent amount is coming from groundwater. So and it's not just temperature-wise that groundwater streams are more stable. It's also chemically more stable, because there's just basically that water is all coming from the same source and hasn't been subjected to a bunch of different changes as compared to like precipitation that's going through the air and then going through the different types of land. All right, let's switch to flow velocity, okay? So when we're talking about stream flow, we can think about lots of different things. And what we see is flow velocity varies within the stream, okay? And essentially where you have is friction in two different places. Now friction between the surface of the water and the air, which granted is not that much, and then with the substrate, which is a lot more. Okay, so if you look at, okay, so what we've got here is velocity, and then this is distance above the bed. Okay, so basically this is the bottom of the stream, and this is the top of the stream. Okay, and what we see is the fastest water is up here at the top. Now, if you have wind, you know, let's say going here to the left, well, if wind is going against the stream, right, you might get a little back up there where the wind, you know, there's more friction because of the wind, and it slows down the water at the top. So this curve might come back a little bit. But, you know, let's say it's not a windy day. Generally what we see is the fastest water is at the top because it's furthest away from the friction with the bottom of the stream. Then as you get closer to the bottom of the stream, as you get closer down here, there's just, you know, there's at the bottom of the stream, there's rocks and pebbles, and there's boulders, and there's wood potentially down there. So just get slower, right? Until, think about that boundary layer where as you really approach the absolute bottom of that water next to the substrate, it's essentially not moving. So what we see is mean velocity is at 60% of the depth. Okay, that means average velocity. If you want to figure out, okay, what's the average velocity of the water throughout the whole water column, you would estimate it somewhere at 60% of depth. So if you had, you know, let me draw, you know, if you have a stream here and you're measuring in the thaw leg, now the thaw leg is remember is the deepest part, and if you want to measure the average flow velocity in the thaw leg, and let's say your depth is 1 meter. Okay, so at 60% depth, you would either go, you know, 60 centimeters down, or from the bottom, 40 centimeters up. Okay, whichever one you want to think about, but it's 60% of the depth down, and that's where you'll get basically the average velocity of the water throughout the whole water column. But remember, if the water over here would be slower than it would be in the thaw leg, because essentially there's you know, if you take it to this graph over here, you know, the shallower water, the water would be right here. So, you know, your maximum that you would find in the deepest part would be over here, but in the shallower part, the maximum speed would be, you know, less there. All right, so now let's move into thinking about how much water is flowing down the street over time. Now, this is what we use to do this is called a hydrograph. Hydrograph is a graph of discharge over time. Now, time is unspecified, and we'll see how that's important later on. But what we've essentially got here are, you know, 24 hours here. You know, we started, I don't know, not in the middle, the beginning of the day, but, you know, different days here. And what we've got, rainfall in centimeters per hour over here, and then stream flow in cubic meters per second over here. Sorry, I drew through that. So what we see is we get some rain. There's, you know, some sort of storm event, all right, from, you know, that night, during this night, right? And there's a lag time between the flood peak, between the rain peak, essentially, or when the rain starts, and the flood peak. Now, that's not necessarily surprising, right? So let's maybe go back to this picture, right? Rain falls down, and you have water infiltrating into those pore spaces first, and then it goes into the groundwater. Or, you know, let's say it just starts raining really heavy right away. You still have to get those pore spaces filled up, and then it takes time for the water to run off and actually make it to the river. So this lag time is super important, or you know, it's going to be there no matter what. Like if you have even if you have like a thunderstorm that comes and dumps a bunch of rain right away, you're going to have this lag time. The more like cement that you have in the watershed, the lower that lag time would be, because the water can flow faster over cement, and there'll be less infiltration into the groundwater, so the flood peak will be higher and the lag time will be shorter. But then what we see is, after some rain event, it takes a while for that stream to basically, it rises faster than it falls. And now that is the reason for that is because the water, it takes time for that groundwater to essentially drain out and drain into the river. So you get this peak due to overland flow, but this stretching out of that stream flow due to that groundwater taking time for that groundwater to drain out into the stream. So I mentioned that time was unspecified, and this makes a really big difference. Okay, so if you look at something like monthly averages versus daily averages, so these are the same graphs. This is the same river, the Kansas River that I did my master's degree on, so that's why I'm using this. And they're both in cubic meters per second. Okay, and what this graph here is basically is daily. Okay, meaning they have, like, every day they plotted what the average discharge for that day was. And what we can see is, so this is from 2014, basically, you had some sort of rain event there, a big rain event in June, a smaller rain event in later September, right? So, and this stream is very, what we would call flashy, meaning it gets a flood very quickly and then goes down very quickly. Now, so this is what you would expect for something for daily data. But let's just take the month of July here, right? So July, it goes from right here to right there. Now, what you see here is in this month you have several different peaks. We had a small rain event right at the beginning of July, middle of July there's another small rain event, and we see a lot of variability here. But what is the average for July there? It's somewhere, right in here. So if you were to put like the averages for January, February might be a little more, May would be lower, this might go a little higher, and then we're going to get higher, and then June would probably be pretty tall, I don't know, maybe somewhere there. But what you're going to do is you can connect these lines then, and what you do is you get a loss of resolution that looks something like this over here. These are monthly averages. So you basically repeated, every January what we see is somewhere around 75 cubic meters per second. Okay, in June we see somewhere around an average of 350. But if you look here, this June is actually in there. It's just one of the Junes that this hydrograph was made, and it doesn't show what June of 2014 was actually like, because June of 2014 had a huge flood at over 900 cubic meters per second. So when you're looking at hydrographs, be sure to think, okay, what is the time scale? Is this daily data? Is it average months? Is it years? It can be very, very different. Then what you need to do is look at the y-axis, right? So if I were to maybe let's do something here. If I were to take this graph, I'm not sure this is going to work, let's see, and spread it out, right, and have it be like the same height, that's not going to show the truth, right? So this is 400 here and 1200 over here. That's this graph. If you were to look at these and be just looking at the y-axis on this daily graph, you might assume that the Kansas River has an average of over 1,000 cubic meters per second every June, and that's not the case. You need to be really careful that the y-axes are the same. So that's why I put kind of scrunched this graph down to make 400 cubic meters per second right equivalent with this one over here. So just be aware of that when you're looking at different hydrographs. So how flashy the stream is looks at hydrograph stability. So basically how stable the flow in the river is. So this stream here showing is the hydrograph of daily data of a stream in Arizona, and you can see, we get these huge increases in floods, but then they go away in just a couple days. This flood right here really probably at max lasted maybe a week, okay? And what we see is, depending on the precipitation regime of the watershed, will determine how flashy the stream is. Also the biome type. So, take a stream like in Arizona, right? It's in a desert. There's not a lot of plants to suck up that water, and the sediment is very porous, bunch of sand and gravel. So when it rains, it's also like a ton of rain all at once. It just flows very quickly through the sediment, gets to the river, and creates these big flash floods. Whereas somewhere like in Wisconsin, we have snowmelt floods. So when we get a flood, it's usually somewhere, March or April, right? And that's because our snow is melting over time, and the flood grows very slowly and goes away very slowly because that snow is just continuing to melt. So in snowmelt-driven streams, we see the hydrograph is much more stable and much less flashy. Also, it depends on the substrate. Okay, so think about how fast the water can flow off of a parking lot versus how fast it's going to flow over a forest with a bunch of like trees and moss and grass and stuff, right? What you get in a forest is, a much more infiltration into the ground, into the water table. So the overland flow is much less. Whereas in a if you have like just a bunch of pavement, a bunch of streets, so think of, just any city, you're going to get, much more overland flow that will fill up the rivers faster and make floods happen quicker. So, what I want to say about the flow regime is the natural pattern of flow in the stream. That is most important, and that's like the master variable. Streamflow is the master variable in any fluvial ecosystem. And when we talk about the flow regime, we got to think about a variety of different things. The magnitude of flow, so how much water is coming down, how that's varied throughout the year, or from year to year. What are the floods like? How often do floods happen? How long do the floods last? When do the floods happen? And how fast do they change? Okay, so here in Wisconsin, we generally get floods, in, again, spring snowmelt combined with a rain event, okay? Whereas in some place like the Great Plains of Texas, maybe through Nebraska, it's midsummer when they get a bunch of thunderstorms coming down and combining in the same watershed to create a big rain event, which then makes a flood. So there's all sorts of different times when floods can happen, depending on the ecoregion, depending on the river itself. When we think about the flow regime, we should also think about base flow. Does the stream dry up, or is there a certain amount of flow that you can always pretty much find in the stream? And then the likelihood of extreme events. How often do these big floods happen? And so when we look at three very different rivers, this is the Mississippi River up near its in northern Minnesota, near its headwaters. And what we see is that snowmelt. This is pretty far north, so we don't get the snowmelt really until April, and we get a snowmelt flood that lasts quite a long time, and then you get late summer, less rain, and then you get more rain into the winter, or into the fall, and snow into the winter, so it comes back up. But this is pretty fast change, but nothing like the Kansas River, where we get these big flood events that are happening. Realize that this is a log scale, right? So these really should be way up here. but these flows are changing very quickly. Then this is the Amazon River, and the Amazon River is the flow changes very, very slowly, right? So if you look at, this is cubic meters per second. That's so these numbers are way bigger than, even here we have 40,000 cubic feet per second, but there's about 28 cubic feet per cubic meter. So this 160,000 is way more. Divide this 40,000 by 28, and you see that the Amazon River discharges much more, and the stream changes much slower through time. So another way that is not a hydrograph to explain how a river flows is called a flow duration curve. Some of you may have had experience with this looking in 258, the field experience class assignment, but what this is it looks at basically how often the river flows at a specific flow rate, at a specific discharge. So what we have is, I'm writing sideways here, discharge over here, and this is the percentage exceedance. Now what this shows you is that it's like how often the river is at a specific discharge or higher. Okay, so what we look at is 100% of the time the river has at least, what is this, 0.3 cubic meters per second. Okay, 50% of the time the river is flowing at 1.6 cubic meters per second, right? So it's a way to visualize long-term flow, and so it's how much time flow exceeds a given discharge. So 60% of the time the flow is greater than 1.3 cubic meters per second. Now, this is useful for hydropower projects. Think about if you were making a turbine that requires a certain amount of flow, because that's what happens is the water is flowing down a stream and you need a certain volume of water to actually spin that turbine to make electricity. So let's say this turbine you need makes is cost effective, right? Like it is actually producing enough energy to make it worthwhile at 3 cubic meters per second. Is this stream, so this one, right, with this flow duration curve, is that stream going to be a good spot for that turbine? So look at 3 cubic meters per second, and what you're going to see is, okay, that means you're only going to be able to have power being produced in this this dam 20% of the time. Okay, and that shows that, hey, we probably shouldn't put this hydropower dam on this specific river, right? Because you don't want your hydropower only being produced 20% of the time. You should get a turbine that works, maybe only at 1 cubic meter per second. You don't only need that much water flowing through. Then it's going to work 70% of the time. And honestly, like you would want your hydropower dam to be working pretty much all of the time. So what you essentially do is take like a bunch of data and put like the discharge for day 1, day 2, day 3, day 4, and then you basically order it from lowest discharge to highest discharge, and then graph that over time, right? So if you sort your data, so you have the lowest discharge, and then all you have to do is basically put the lowest discharge first, and then sort that in a decreasing scale from 0 to 100, and you will get your flow duration curve. So when we look at flow duration curves, then if you see differences in the shape of the curve, you'll get to know something about the stream, right? So what this blue line is showing is that there's a high flow for a short period. And what that's a flashy stream. That would be a hydrograph that would look, kind of like this when we have time here and discharge. So that's right here. A snowmelt stream, that's where you get in the summer, or you get these long-lasting floods. So here maybe would be the spring, and here is the summer, and then the fall. So something looking like that, right? Where what this is showing is essentially this plateau up here is saying that there's high flow for a relatively long period of time, and that's reflected in this part of the hydrograph. Okay, and then let's say you have a stream with an extremely stable hydrograph. So again, here is time and here is discharge. Essentially you get no changes in the discharge over time. So this might be like a stream that's coming right out of a spring, like right at a spring. You might have the flow duration curve looking something like this red line here, which is pretty much horizontal. Now, when we think about the flow regime holistically, what we see is that the flow regime drives the ecology of the system, and native species are adapted to that natural flow regime. Any alteration usually affects those native species negatively. When you alter the flow regime, you allow other species that are adapted to that altered flow regime to come in and invade. So each individual species is adapted to I wouldn't say know, but it's adapted to survive in a given environment. So any change to that is bad for those organisms. Okay, so think about this stream here, right? And this is a little hard to think about, but we've got 1930 here and 2000 here, so 70 years of data. And what you've got here is it's a backwards, so here is New Year, and you're going kind of through the year this way, right? And then it wraps around here. What they're doing here is doing water years. It's kind of confusing. And then you got discharge, okay? So in the mid-60s, they put in a dam, okay? And if you look at the stream before, what you've got is a really flashy stream that had floods in the summer, somewhere between April and September. Okay, so you have this period of time in here where you have a lot of water going down the stream. Now what they did with this dam is they put dams on to basically stop the flow of water, so we didn't have these big damaging floods to the surrounding landscape. But what did that do to this, this October through April, right? That winter period now, rather than having really low flow, has a moderate flow throughout all of these years. Yeah, maybe there was a drought here in the early 90s, but essentially what dams oftentimes do is they lower the magnitude of floods, but they spread the same amount of water still needs to go down the river. It's just spread out over a longer time. So if you look at that on a hydrograph, on just an individual hydrograph, what you would see is before there would be these big, tall floods that would last for a long time, and then a lot of lower flow. Sorry, I should label these axes time and discharge. But now what happens when you put a dam on a river? You would have a lower flood that is then lasting a longer time. So like the area under these curves, that would be the total amount of water going down, is the same, except when you have a dam, the magnitude is lower, but the amount of time that there is water is extended. One other really damaging thing to the natural flow regime is this thing called hydropeaking, okay? And what hydropeaking is is a change in stream flow due to a hydropower calling for power, okay? Or a hydropower plant needing power. So they basically open the floodgates and let the water flow and to speed up their turbines, okay? So this is a stream, I think this is somewhere in Colorado, I forget exactly, but you can see this is the same day. This is like early in the morning, and then this is later in the day when everybody's using their electricity. So, you know, if you're a fish that's living in here, oops, bad fish drawing, but if you're a fish that's living in here, the drastic differences of these flows are, you know, just a couple hours apart, are extremely hard to handle. And what happens is essentially, the overnight, nobody's using that much power, right? Like everybody's sleeping, they've all got their lights off, they've turned their heat down potentially. And then everybody, you know, 8 a.m., so that's right here, everybody starts waking up and they turn on their lights, they turn on their TV, they're using electricity, and the power demand increases drastically, okay? And power demand, if you're getting that energy from hydropower, means you basically have to allow more water through the gates to spin those turbines. So you see there's this big peak during the day, and then around at 10 p.m. when everybody starts turning off their lights and not watching TV anymore and using electricity, the power demand goes way down. So, you know, I'm talking about power demand, but this is actually just discharge in the stream, and that's it. You know, power demand is going to mirror discharge if their energy is gotten from hydropower, unless we have like battery backups, which, you know, generally most people don't. Those power companies need to be producing enough power such that it meets the demand. So this is like the most extreme example where you're increasing flow here by, you know, 100 times more flow than at the daytime versus what would happen during the nighttime. And no organism is basically able to be adapted to that, and changes that quick just don't happen in nature. It's going to be a big problem for a lot of organisms. All right, with that, see you later.